Hey, Cecile, the mic is yours. Thank you.
Welcome to Quantum Photonics. This is a very memorable room. This is Eclipse Day, and I think a lot of people are also out. I'd like to introduce our speaker, and also the topic here. So, in a recent publication in Nature Communications, Dr. John Bruce Murray, Robinson Tchaikovsky, along with their team, had unveiled a pioneering technique that promises to revolutionize our perception of obstructed environments. Their research focuses on ingenious utilization of everyday digital cameras to reconstruct highly accurate, full color, three dimensional representations of areas concealed behind obstacles. This breakthrough not only holds immense potential in averting car accidents, but also extends its utility to law enforcement operations, search and rescue missions, and strategic military endeavors. By harnessing the subtle shadows cast on nearby surfaces, the algorithm made by our authors transforms ordinary environments into reflective canvases, unveiling hidden regions, objects, and even entire rooms. What was once confined to the realms of science fiction is now tangibly available. Prior to their work, the prospect of such reconstructions was limited to specialized, costly equipment. However, with their technique, the barrier to entry is significantly lowered, rendering this capability accessible without exorbitant expenses. While this technology is still in its nascent stages, its potential applications are vast and varied, and this is from enhancing the safety and situational awareness of self driving cars to aiding law enforcement in critical scenarios. The possibility of this are truly transformative. To introduce our guest speaker, uh, yeah, our guest speaker, Dr. John Bruce Murray, had received both his mechanical engineering degree with honors in 2012 and the PhD degree in 2016 in electrical and electronic engineering from Imperial College London. And while at Imperial College London, he received the Institute of Engineering and Technology Award in 2012 for Best Overall Performance in the Mechanical Engineering degree, and that the Maurice Hancock Award in 2008. In March 17, he joined the Electrical and Computer Engineering Department of Boston University in Boston, Massachusetts as a postdoc research associate. In spring 2020, he joined University of South Florida's Department of Computer Science and Engineering as an assistant professor. His research interests are in computational imaging, vision, and inverse problems. So, without further ado, I proudly bring you our special guest speaker, Professor John Bruce Murray. So, John, welcome to Quantum Photonics.
Thank you so much. Thanks for having me. Thank you to as well to Bob and Dassel for, as well as yourself, Cecile, for inviting me to give this talk. I'm super excited to be here, and it's interesting. Well, kind of a nice bit of um, good fortune, if you want, that I'm given this talk where I'll talk about exploiting shadows, right? And given the current uh, situation with the eclipse, um, it seems quite um, fitting. So, you may have been staring at shadows of the sun's crescent, and so on. So, anyway, so today my talk is on, as Cecile kindly introduced, my talk is on three-dimensional imaging without line of sight. So I'll, so because it's an imaging problem, I thought it was hard it would be hard to do without actually having visuals. So I prepared a few slides with as few words as I could get away with, but with lots of pictures. Okay, so hopefully you can follow follow me along by looking through the slides as well. So this work started actually in my during my postdoctoral position at Boston University in 2017, and it's since then it's been something that's kind of close to my heart for various reasons, for the applications, for possible applications it has, and also for because it's a simple problem to state, right? It seems like science fiction. We want to see around obstacles. Okay, that's it's very simple to state. Pretty much everyone down to kindergartners can understand the statements of the problem, and also most people can appreciate that it's a very difficult and challenging problem to solve as well. So I like that aspect. So those are the kind of things that have drawn me to the problem. Um, because it's simple to state, um, challenging, and essentially has a lot of applications in real life. Okay, so the outline of the talk, I'm going to tell you what non-line of sight imaging is, why we care, why do we want to do non-line of sight imaging, um, it's been achieved, and how we achieve it, and then what's next. Okay, is the problem solved? Should we just stop looking at it, or is there more to do? Okay, so um, I'll kind of start with the problem statement, motivation, key premises for the solution idea that we had. Um, and these points kind of form the outline of my talk, which is summarized in slide 2. Okay, so what exactly is non-line of sight imaging? Why we may want to achieve or perform non-line of sight imaging? How do we achieve this in my lab? And then where do we go from here? So starting with conventional photography. So in conventional photography, we rely on unobstructed light paths between your camera and the scene of interest, or the viewer and the scene of interest. Okay, so if we take a look at slide number 3, you can see a photographer trying to take a photo of two people. Okay, so there's the line of sight between the photographer and the scene of interest. Um, you know, however, um, this may not, the same may not be true. Okay, imagine there's that line of sight is obstructed. Okay, so in certain situations you may not have direct line of sight, so you cannot not draw a straight line between yourself and the scene of interest without having that line intersect, pass through an obstacle. Okay, so there's no line of sight, so to speak. So should we give up? So what if that this you don't have line of sight? Should you give up? Throw your hands in the air. This is an impossible problem. Well, that's one approach you could take. But we decided to see what we can do in that situation. Okay, we realized that whilst you may not have direct line of sight, there may be surfaces um, around that do. Okay, so if you take a look at the slide number 5, you can see a situation where the observer doesn't have direct line of sight with of the people that he was intending to take a photograph of. They're now standing behind a wall. However, there are surfaces that do have line of sight. So he can take photos of that surface, okay? And from photos of that surface, we want to actually compute or estimate what's hidden. Okay, so what's contributing light to that surface? Okay, so lots of or since the inception of this problem, say something like 14 years ago, um, there have been a number of approaches. Okay, so a few approaches have appeared. And mostly these have relied on very expensive or and specialized hardware. So the key approach or the leading approach was using so-called active imaging. So in active imaging, which is summarized in slide number 6, the idea is to use a laser pulse um, that you essentially send that laser pulse towards essentially a photon. You send that photon towards a surface. It bounces off that surface, scatters in all directions, Some of it goes into the hidden scene, so the region that's obstructed from view, um, and then interacts with objects in that obstructed area. And some of that light gets reflected back onto a visible surface and then back to your camera. Okay. So by timing how long it takes that photon to do um, that kind of three bounce travel, so that three bounce journey. So first bounce being from the visible wall into the hidden scene, then the second bounce being from the hidden scene back onto the visible wall, and then the third bounce is from the visible wall back to your camera. So by timing how long it takes for that photon to travel, you can imagine this is pretty fast, right? Because we're talking about speed of light, right? So you can imagine you had a very expensive stopwatch, and we have some of those. So we have an equipment that can actually time that um, photon in flight. Okay, you could actually, depending on the time of flight, okay, so the time it takes the photon to go into the hidden scene and return back to your camera, you could actually make an estimate for where an object might be, okay, in some hemisphere. Okay, so um, dependent that time relates to the radius of that hemisphere. Okay, so you can then repeat this for many different locations, and by doing so, you can gather a lot of information about the hidden scene. Okay, but you can imagine that this is requires a lot of really expensive equipment. So you need essentially a very expensive stopwatch. You need a single photon um, a detector, a single photon counter, um, and an ultra fast laser, okay, to be able to achieve this. But regardless, you can get a very good idea of what's hidden from you. But this can take a long acquisition time. So it takes maybe something like several hours to actually gather that information that you need. Um, so we wanted to simplify that. The question we posed to ourselves um, in my lab was, can we exploit naturally existing light, okay, occurring all around us, um, and knowing the physics of how light travels, could we exploit that to do imaging? Okay, so and we want to achieve this using an ordinary digital camera. So we take on slide 7 here, we can kind of see a setup of that of the situation we're in. So we have a camera that has a certain field of view. So it has a view of some visible surface. But the special thing about that visible surface is that that surface itself does have line of sight to a region that may be obscured from you. Okay, so this is the problem we're trying to solve. In fact, this situation occurs all around us. Okay, so essentially, all around us, for instance, you can imagine it in a hallway. Um, there's typically a wall that blocks your view of some region. You could also imagine in um, everyday driving scenarios or situations when you're pulling up to an intersection, the crossroads may not be completely visible to you. Okay, so there may be occluded regions, okay, or hidden or obstructed regions. You could also imagine other situations in driving as well, where maybe there's a parked idling vehicle, idling a van or bus, and you don't know what's happening around the other side of the bus, right? Or the idling vehicle. Okay, so for instance, you can imagine a pet or a child might be on the other side, and they may be walking into the path of an oncoming vehicle. Okay, so we want to be able to kind of anticipate all of these situations, and these are some of the use cases that we had in mind. Okay, so in all of these situations, you might not have direct line of sight, but there are surfaces all around you that may have line of sight. And in everyday situations, those surfaces are not mirrors. If they were mirrors, then the problem is easy. Okay, so they're not mirrors. We want to somehow use computation or algorithms, if you will, to turn those surfaces into mirrors. Okay, so on slide 8, there's a nice kind of graphic that shows essentially our idea. Okay, so summarizes what we do. Okay, so for any given hidden scene, the physics of how light travels is pretty much well known. So we know how to essentially um, mathematically simulate, or we mathematically understand how light travels. Okay, so we can, for any single light emitter, we can tell you, or we can render essentially its contribution to a any surface. Okay, so given that we know this physics, we can somehow we can mathematically render possible observations. Okay, possible images that you would obtain of a if you took a photo of a blank surface. Okay, so um, and on that surface we can essentially um, we can essentially characterize the light distribution on any surface. Okay, visible any visible surface to the observer. Okay, so the idea is, given that we know this, we want to say, well, given any observation, okay, given some photograph of a visible surface, can we go back and somehow predict what the most likely hidden scene configuration would be to lead to this measurement that we have, this observation image? Okay, so that's kind of the high level idea. Okay, so let's kind of let's dig a little bit deeper. So on slide 9, I'm providing a photo of um, the core ideas. Okay, so looking a little bit deeper. So we're exploiting these subtle variations in shadows. Okay, to be able to do this imaging. So on slide 9, there's a hidden scene. So um, on the far side of the blue wall, and imagine that that blue dot, okay, on the hidden in the hidden scene, is emitting light in all directions. Okay, so it's just one point, one tiny light bulb. You can imagine a candle, a lit candle, or an LED. Um, it's it's emitting light, and because of the wall, um, it there would be an obstructed region. Okay, so that region does not receive any light. Okay, whereas there would be another region that does receive light from that point source. Okay, it's from that LED light source. Okay, in fact, through simple geometry, we can figure out where that light source is. So I'll show you the top-down view on slide 10. Okay, so it's on slide 10. There's a top-down view of the illumination pattern, so the light contribution onto the visible side, so the lower half of that picture on slide 10, okay, shows a light distribution caused by the point, um, the LED light source in the hidden scene. Okay, imagine we're standing on the lowest half of this room. We're outside the room, so we're standing on the lower half of this figure. What we see on the floor beneath us is this light variation. That's some portion is completely dark, whereas other portions have these subtle gradations of light. Okay, from that observation, we can immediately somehow intuit that, hey, there must be some light coming from the hidden scene. Something must be emitting light. And by drawing a straight line between that point, okay, by extending a straight line at the edge of the shadow, so at the boundary of the shadow, okay, the boundary between the dark region and the illuminated regions. Um, by extending a straight line, we can tell where the location, okay, in angle of that light emitting source is. Okay, so now, given that, I wanted to, I don't know how interactive we can be here, but on slide 11, there's a little puzzle. Okay, so there's a puzzle that shows the original situation. Okay, and then on the right hand side, there's a new figure where with a kind of question mark, okay, obscuring the hidden light source. Okay, so the position of that light source is hidden from you, and I want you to guess, okay, where you think that light source would be. So I'll give you a moment. So there'll be a little pause, okay, for 10 seconds. Okay, so on slide 12 you can see the answer, okay, to that. And if you guessed correctly that it must lie on a straight line that intersects the boundary between the illuminated portion, okay, of the lower half of that figure, um, and the in shadow portion, then you're right, okay. So that you can see the blue dot there is at something is somewhere around 0.4 for along x and zero point 0.2 along y. Okay, so this is the key idea. Okay, so the edge, okay, the wall edge that actually prevents our view, prevents us from seeing into the hidden scene, is actually giving us information about the hidden scene. Okay, so it's just we need to think about a little bit more carefully. These shadows are all around us, but we never take notice of them. In fact, our brain is somehow conditioned to remove them. Okay, so we would never take notice of them, but they're all around us, and they're super informative about um, things that may be obscured from our direct view. Okay, so this idea was actually exploited in an original work um, from MIT and this was around the time when I was at Boston University. Okay, so these fellow collaborators actually figured out a way to solve this in 1D. Okay, so what they created was a 1D, a one-dimensional photograph, if you want. Okay, so they could basically tell you in angle where objects are in the hidden scene. Okay, so this is somehow useful because, well, you can tell the angle, but maybe you can't tell how far away things are. But maybe the angle is already well, the angle is already good information to have. Okay, and you could, they were able to demonstrate this in, in really extreme conditions, where by utilizing some techniques in image processing and so on to amplify that signal. Okay, so in everyday situations, these shadows are super faint, so they're not as pronounced as the ones we saw in slides 11 and 12 and so on. Um, they're really subtle. Okay, so on slide 14, you can see an example. Okay, so this is there's a small box and insert um, in a red with a red boundary. Okay, so that's a typical photograph. So that from that photograph, you can see a subtle variations in illumination, some shadowed regions. From that photograph, we were able to, in a prior work, we're able to extract 2D information. Okay, so we were able to reconstruct a plan view, so a bird's eye view, if you want, of the hidden scene, okay, from just a photograph of the floor. Okay, the special thing to remember here is that the floor itself has some portions of the floor are visible to the hidden scene, whereas some portions are obscured from the hidden scene. Okay, so that and this is those obscured portions are in shadow, whereas the unobscured portions are illuminated by the hidden scene. Okay, so from those measurements, the one, for instance, in the red box, we were able to reconstruct a 2D plan view with color information. Okay, so the next step was then, well, how do we, how can we extend this to 3D? Can we actually try to get 3D information? Okay, the difficulty here in these 2D reconstructions um, is in the fact that the range or the radial fall of how far the objects are um, in the hidden scene, okay, from the door edge. Okay, so there's a highlighted edge in that slide 14. Okay, that edge is is the edge of the wall that essentially gives us the shadowing. Okay, so it basically allows you to is so extending from that edge to the left, essentially the wall blocks light. Okay. So the key thing, that edge essentially gives us angular information. So it tells us um, at what angular bin around the edge. Okay, so you can imagine some angle going that's pivoting around the red wall edge. Okay, it gives us information about the hidden scene along that angular trajectory, but it doesn't tell us how far from that red edge, so range from the red edge, the objects in the hidden scene are. Okay, to kind of see why this is a challenging part of the problem. Um, in slide 15, you can see three situations, okay, where there are three, each showing a this LED, okay, LED, this point light source, emitting light in all directions, um, but some of that light gets blocked by the wall, okay, and some of it goes through. And in all three situations, each of the three situations, that LED light is sitting at a different range. So some of it, in one situation, it's quite close to the wall's edge. In um, in the very first situation, so that the figure to the left is very far from the wall edge. Okay, in the middle image, it's not too far but not too close, and in the third image, it's even closer to the wall edge. Okay, each of the three situations produce a certain measurement, so a certain shadow or penumbra pattern on the floor, and our job is to look at those shadows and be able to guess where the hidden uh, point source is. Okay, the hidden light emitting source is in the hidden scene. Okay, this is quite challenging to do, especially at further as the source moves further and further away. Okay, so you can see this, and because in the first two pictures, the light distribution on the floor look very similar, whereas in the third situation, it's a little bit more different than the other two. Okay, so that shows some of the challenging aspects in reconstructing range from these so-called soft shadows or photographs of soft shadows or penumbra photographs. Okay, regardless, we were able to, using some signal processing techniques, tease out the information um, to, to perform a 2D full color reconstruction, but we were limited to simple scenes. Okay, so our reconstructions were of fairly simple scenes um, that are um, not too complicated in the sense that um, they don't have too much structure. They're kind of like barcodes, if you want, thick barcodes or vertical stripes. But so the idea is, we could see that, well, the core idea had um, had some merit, but we were still limited in our reconstructions, and we wanted to see if we could push this further. Okay, and this is um, what spawned the idea of trying to essentially get to three-dimensional imaging. Okay, so try to reconstruct in 3D, okay, the hidden scene. Okay, so that's the current work, okay, um, that we published in Nature Communications, um, and that's will be the main focus of this talk. So I'll talk to you about some of uh, the ideas from a high level, and then we'll go into maybe some um, mathematical considerations, some of the technical considerations that made this work. Okay, so to do this, let's um, take us kind of review the prior work. Okay, so on slide 18, we essentially exploited one edge to get this so-called azimuthal resolution. So resolution in angle where the pivot is around the vertical edge of the doorway. Okay, of a doorway or a wall. Okay, or a corner if you want. So my student and I started thinking of different edges that could actually offer additional resolution. Okay, so a complementary information if you want. Okay, we already know how to solve the issue, the problem when um, for azimuthal information, so pivoting around the vertical edge. And then we realized that, well, at doorways, okay, you have this additional edge, so the horizontal edge, and one could actually exploit this horizontal edge. Okay, at least that was what our line of thinking. Okay, but we ran into a few challenges that we needed to tackle by developing essentially a new mathematical framework. Okay, okay, so to kind of talk about this orientation a little bit more, to give you an understanding for why we believed it would help us, and of course it did work in the end, but it took some time to get it to work quite as well as it currently does. Um, so if you think of the two edge orientation, so imagine the top of a doorway. Okay, you have the horizontal edge, which is at the head of the doorway, and the vertical edge, which is on the side of your doorway. Okay. And to be able to exploit those two edges, you essentially need to look up at the ceiling. Your photograph needs to be of the ceiling. Okay. So from that photograph, you're going to kind of use our computational algorithms on that photograph to reconstruct the scene. Okay. So your photograph is of the ceiling. And given this two-edge orientation, to help us visualize things, I'm going to kind of turn it upside down. So pretend we're looking at the floor, and there's a horizontal and a vertical edge. Okay, so on slide 19, there's a nice picture of this. Okay, so in slide 19, you can see a picture where there's again this point source we have at the hidden room. So it's the blue dot. Okay, that blue dot, we're going to move it around that ellipse. Okay, there's a blue line that shows an ellipse in 3D. And that blue dot is going to move around the around that ellipse. Okay, in its first position on slide 19, you can see the shadow that's cast on the floor. It looks like a right trapezoid. Okay, it has this trapezium shape where much of the much of the floor or the ceiling. Okay, remember I've turned the ceiling upside down, so we're still looking at the ceiling. Um, much of that observation is in shadow. Okay, so it's the shadow of the doorway. Okay, of the walls containing the doorway. Okay, and that shadow is caused by the fact the light coming from the blue dot. Okay, so that LED light that we have in the hidden scene um, is emitting light in all directions. However, in some directions, that light gets blocked. Okay, it gets blocked by the wall and by the head of the doorway. Okay, so the horizontal um, portion of the wall. Okay, and comparing the the observation. Okay, so that's the shadow pattern. Okay, the observed shadow pattern, uh, comparing it to a different situation in slide 20 where that light source has moved to a different location. We can see that there's a slight change in the shadow. Okay, in the pattern of the shadow. Okay, and even more so, there's a more drastic change if we look on slide 21, where this point is now at a different location on this ellipse. Okay, you can see a completely different um, pattern. Okay, a completely different shadow pattern created by the point source. So the reason I showed this is that there's some way to tell, okay, by looking at the, if we were only allowed to look at this shadow pattern, so if we're only given that information, there is some way, there's some hope in relating that information to the location of the blue dot. Okay, of course we want to be able to do this computationally, so using a computer or automatically as well. Um, but there's some the core intuition what I'm trying to build here is that this shadow pattern contains a wealth of information about the hidden scene, and it could potentially give us 3D information. Okay, so kind of reorienting back. Okay, so I'm going to kind of turn the ceiling back to where it should be. So the ceiling is now at the top. Okay, on slide 22, you can see the full situation that we're in. Okay, so it's a picture on the left that shows the full situation we're in. You have an observer with his camera. Okay, he takes a photograph of the ceiling, and from that photograph, he wishes to compute a reconstruction of what's in the hidden room. So one classical way to do this is to say, well, um, I'm going to set up a problem where I'm going to divide up that hidden room into voxels, okay, into these tiny cubes, and I'm going to carve out cubes that don't. I'm going to remove cubes that don't emit any light, okay, so and essentially shave them off to give me a 3D rendering, okay, so just a 3D depiction of what the room is, okay, where only portions with objects in them will have a voxel. Okay, so there'll be some colored voxel. So you can see on the right hand side, and I have a voxel, a grid of voxels. So these voxels are essentially tiny cubes, okay, um, that are arranged um, um, in a grid. Okay, so equally spaced grid. Okay, so if there's no light from that specific portion in the hidden scene, okay, in the hidden room, we remove the cube. Okay, we take out that particular voxel, and only voxels that will be left are voxels that have a hidden scene object in that location. Okay, so that's one kind of way to think about um, going about doing this. So you want to try out many different configurations for these cubes, okay, and pick the one that best explains the observation that we make. So the photograph that we captured on the of the ceiling. Okay, so um, the camera field of view, so that green um, kind of that green rectangle there is the camera's field of view. Okay, so we this is essentially what we tried at first. So we tried to kind of solve this problem in so-called Cartesian coordinates. So Cartesian coordinates is the coordinate system that we're used to. Okay, so there are many other coordinate systems such as polar coordinates and spherical coordinates and so on. Okay, so for lots of imaging problems, typically we stick with Cartesian coordinates because it's very natural. Okay, it's the one that's most natural to us. For other problems, there may be other coordinate systems um, that would be more useful, and in fact, that was what we found. So there's a different coordinate system that's not that at least not to my knowledge um, that is not popular or at least known um, at the, prior to the time we did this work. Okay, but nonetheless, our analyses led us, or our mathematical analysis led us to this coordinate system. Okay, so the idea is the coordinate system is as follows. It deviates from the Cartesian coordinates. Okay, um, and on slide 20, um, 24, okay, we start to lay out, you can start to see um, the idea behind our coordinate system. So the idea is that we have um, any single point in the hidden scene is identified by three numbers, okay, by some 3D vector. Okay, so the first entry in that vector is the range. Okay, so how far that point is from some origin, and the origin we're picking here is the one at the apex of the horizontal edge and the vertical edge of the door frame. Okay, so to the left. Okay, so the one closest to the field of view of your camera. Okay, this coordinate system uses essentially three numbers. Okay, similarly to a Cartesian coordinate, there's an x, y, z. Okay, so each of those are essentially for given three numbers, you can uniquely identify a point in Cartesian coordinates. Okay, and similarly, given three numbers in our coordinate system, we could also identify a unique point. Okay, so we called our coordinate system projected elevation spherical coordinates, and perhaps the reason we called it this will become clear as I talk. Okay, so this our so-called projected elevation spherical coordinate system is for any point in the hidden scene, we can identify it by three numbers. Okay, the first number being the range. Okay, that range is distance from the origin to the point. Okay, so imagine the straight line distance, the shortest path between the origin, which is the horizontal edge of the door frame, and the vertical edge of the door frame, so that where they meet, okay, that the distance from that point to the a point in the hidden scene. So that's the range. On slide 26, the next number, which is the second coordinate, that's the azimuthal angle. This is the same angle as in spherical coordinates or in polar coordinates. And it's essentially the angle between the straight line um, that's along the xy plane, okay, um, the points projected onto the xy plane, the, the angle between that straight line and the x-axis. Okay, so that's the azimuthal angle. And then similarly, we essentially define the projected elevation angle instead of it being the usual elevation angle which we're used to in spherical coordinates. Instead, we do a similar projection, but this time we do a projection onto the YZ plane. Okay, so the angle psi here is the angle between the straight line that joins the origin to the hidden scene points projected onto the YZ plane, um, and uh, the angle between that line and the y-axis. Okay, so I've shown this on slide 27. So you have all of the coordinates on slide 27, um, which show rho, theta, and psi. Okay, so these are the three numbers. And what's special about this coordinate system is that it allows this so-called nice property of information orthogonality. Okay, which explain in a couple of slides. Okay, in a nutshell, this property allows um, essentially changes in along one axis. Okay, so say it's changes in range rho does not cause any effect on any of the other coordinates. Okay, um, so I'll show this pictorially, and or similarly changes in theta, so azimuth or projected elevation, do not impact the other coordinates. Okay, so to see this, um, I have on slide 29. Okay, um, this should be animated, but it isn't. But on the very first column, okay, you can imagine this dot moving in such a way that range and its range and projected elevation angle, so psi, so rho and psi, essentially kept fixed. Okay, the only change that occurs when this happens will be changes in the kind of the slanted path of that observed shadow. Okay, and similarly, when the the source is moving, the hidden scene point source is moving in the hidden scene, such and moving in such a way that only the projected elevation coordinate psi changes. The only perceived changes on the observation or in the observation will be changes in the height, okay, so the horizontal position or that straight, the kind of top of the trapezium, if you want, or of the trapezoid, okay, the top part of the trapezoid. Okay, only that only the height of that trapezium changes essentially. Okay, so it either gets taller or it shrinks down to be thinner. Okay, so you can see that between the second photo, so the second column and the third column photo. Okay, so all of these changes. So when the source moves in a certain way, so if it moves along rho, only one particular property changes in the observation. And when it moves along theta, only a certain change happens in the observation and in the observed shadow, and similarly for the projected elevation. Okay, so um, instead of using a discretizing on a Cartesian grid, which we initially tried and failed, okay, um, we tried doing that and we didn't get anywhere. And the reason is because of this information orthogonality property wasn't satisfied in Cartesian, but it is in this new coordinate system that we designed. Um, so instead, we designed these voxels, okay, these actually, we stuck with surfaces to begin with. We designed these so-called surfaces that are described on a projected elevation spherical coordinate system. Okay, so our specially designed coordinate system. Okay, remember, like every kind of 3D coordinate system, our system is also identifies uniquely a 3D point given um, given three numbers. So the first number is range, the second number is the azimuth, and the third number is the projected elevation. Whereas in comparison to, for instance, a Cartesian system, the first number is the x, and the second number is the y-axis, and the third number is the z-axis. Okay, um, where you're moving these like straight line orthogonal grids. Okay, so in our system, we could actually then say, well, given that we could essentially represent a hidden scene point by those three numbers, okay? And if we discretize finally, so instead of creating these kind of cube for voxels, instead we created these projected elevation spherical coordinate type surfaces, okay? It's kind of tiny facets, okay? um, by discretizing, okay, in a similar way that we would for the Cartesian system. Okay, so we could say we wanted equal thetas, okay, so equal azimuthal angles and divide along equal projected elevation angles. Okay, that would essentially give us these surfaces that I show on slide 31. Okay, so on slide 31, there's a picture of all of these of a specific grid in our coordinate system, and this grid has 10 elements, 10 by 10 elements. So I've divided of the elevation, the projected elevation angle into 10 equal angles, and the azimuthal angle into 10 equal angles, and I've kept the range fixed, okay, so that you can see the surface. Okay, the key thing to note here is that I've done this so that one could visualize what's going on, but in reality, we're going to make this, a large discretization, something like 120 by 120, maybe 256 by 256. So in that situation, these things, and you can no longer appreciate the shapes of these facets. So they essentially become points. Okay, so they become points in a point cloud, and those are the types of reconstructions you'll see when we get to the results. Okay, so based on our discretization of the hidden scene, so we could actually now formulate an inverse problem. So an inverse problem essentially says, well, we try to tackle um, the problem of saying, hey, given these observations, given this observed image, observed photograph, what's the most likely hidden scene that could explain, that could have led to this? Okay. So on slide 33, there's the so-called um, forward model. Okay, this forward model essentially captures how light travels. Okay, on the left, okay, which hand side of that equation, we have y, which is the photograph that you take. Okay, this non-line of sight photograph, and you can see in that photograph there are some kind of subtle shadows changes in intensity, and so on. Okay, A here, on the right hand side of that equation, A represents the so called physics of light transport. So, given any point in the hidden scene, if it were emitting light, we could tell you what the contribution of that point would be in the observation image, okay, by using this A matrix. Okay, so it essentially captures light transport, and we know how to do this. This is we're not this is not our innovation. This is well known physics. And X um, is used here to represent the hidden scene. Okay, so the unknown hidden scene. Okay, in this case, if we assume that we knew it and it was that photo on the right hand side, then um, it would produce on the visible surface, okay, the visible ceiling, the observation image on the left hand side of the slide, the top left hand side of the slide, 33. Okay, the key idea here is that we parameterize, so we say that the hidden scene is described by this x and rho. Okay, so for every, where rho is the range from the origin for every point in x. Okay, so for every facet, every um, surface element shown in that discretization on slide 31. Okay. Okay, so the next step is, well, given that we have an observation y, we know how light travels, can we find x? So we know y, we know a. Can we find x and rho? Okay. In fact, if we found x and rho, that would essentially characterize the entire hidden scene. So we started by saying, well, given the way we set up the problem, given the so-called information orthogonality property that I alluded to earlier, okay, um, that led to our coordinate system, this projected elevation spherical coordinate system, given that property, not knowing the range has no impact on X. So we could just choose anything for rho. We could set rho to be random or just some fixed number. And we did that. So we said, well, this is it's not the true range for the hidden scene. Okay. For the objects in the hidden scene. In fact, the objects in the hidden scene are at random points. Okay. Random ranges. And we're just going to initialize it to be just some fixed value and solve for x. Okay, so essentially this boils down to a standard linear system. Okay, so a linear set of equations, simultaneous equations, where you know y, you don't know x, you want to find x, right? So this is a standard thing, but it's in our problem it's not so. One must make additional assumptions to be able to make this problem so-called well conditioned. Okay, so it's actually a little bit of a challenging problem still, but it's the easier of the challenge of the challenges here. So we can solve for x in principle, and the way we do it, we solve this so-called L1 regularized inverse problem. And the idea is that we know that in reality, in any room, okay, look around the room you're in now, you'll find that it's mostly empty space. Okay, so most of the points in the areas in that room, most of the points or uh, is empty. There's nothing there, and there are only a few regions that are actually occupied an object, right? So that one could say that that room is so-called sparse. Okay, so the idea of this so-called L1 regularization, okay, so this constraint here is to enforce sparsity. That the uh, i- okay, so to find a solution that is in because in many situations most of the room will be empty. Um, so we and basically sparse. So we want to find a solution that has mostly zero, so it's mostly empty. So, but some voxels or um, uh, some positions are occupied. Okay, there are standard ways to solve that. Some of those algorithms, like the FISTA, fast iterative shrinkage thresholding algorithm, ADMMs, and so on. There are many different ways to solve this problem. Okay, so in fact, we did that, and we got a nice, initial reconstruction where we were able to identify. If you look at slide 36, we're able to identify the location of these three objects. Okay, in angle. Okay, so here we're showing a top-down view, and we're able to tell that where the objects are in angle. So this is a 2D reconstruction. Okay, so at best, we've kind of, at least we know we can still solve the 2D problem. So with these two edges. Okay, so the biggest challenge that we faced was then extending this beyond 2D. Okay, so to try to do this in 3D. Okay, so the step, which is simple, is it's saying, hey, now I know X, I want to figure out what rho is. Okay, what the values for rho are. So essentially the depth. Okay, how far each of those surfaces I identified for the hidden scene. Okay, each of those points, how far are they from the origin, from the apex of the door frame, or one of the vertices of the door frame. Okay, so to do this, we essentially used our initial estimate for X, and then put that back um, into the problem and try to solve for rho. Okay, so the ranges. Okay, so in fact, this was one of the more challenging aspects of the problem that took us a while to crack. Okay, it's simple to state, but it was challenging to crack, and it essentially made us um, develop this new coordinate system, and a new way for processing the data. Okay, so I'm going to summarize now that algorithm that we use to process the data. So I'm going to show you in a series of slides. So starting with slide 39. Okay, so in slide 39, this shows kind of a full workflow of our algorithm. So step A, we get our photograph. So you take your picture. Okay, that's easy to do. Point your camera at the ceiling and take a snapshot. Okay, then we take that photograph. It's colored, so a photograph has a red channel, a green channel, and a blue channel, basically telling you how much um, the relative intensities of each of those channels in your photo. Okay, and for each of those channels, so red, green, and blue, we solve the so-called linear inverse problem. So the L1 regularized inverse problem that I spoke about a few slides earlier to figure out the essentially 2D reconstruction, the overall shape of the hidden scene. Okay, so we do that for each of the three channels, and then this gives us a red channel of the hidden scene, a green channel of the hidden scene, and a blue channel of the hidden scene, and we can combine those. So that combination is showed in slide 40. Okay, labeled C, okay, the figure labeled C in slide 40. Here we get this reconstruction that shows kind of a white mannequin, a little blob on the floor that's reddish, and then a ring of sorts. Um, so we have that, and um, essentially the idea then, the next step is to then say, hey, for each of these objects, okay, so what is where should this object be placed in range? Okay, because we know objects in reality are typically continuous, right? So they're continuous surfaces, um, and then they're kind of smooth and continuous, and then you have these abrupt changes. So they're discrete objects, okay, occurring in reality. So each object will be sitting at a specific position. So that's essentially the observation that we exploit next. Okay, so then we say, well, on slide 41, we know there are four different objects in this case, okay, in the room. And for each of those objects, we're gonna now solve for their ranges, so for their positions. Okay, and that's on slide 42. Okay, so we solve a new problem to get the ranges for each of these objects in the hidden scene. Okay, and once we compute those ranges, we could actually then display things in color, and we're basically done. Okay, so now what we see on slide 43 um, is we're essentially painting back onto the ranges, okay, each of the clustered objects, each of the objects that we found um, in our initial estimate. We say, hey, object number one, you're at, say, range equal to 5 meters. Object number two is at a range 3 meters, and object number one is at 4 meters. So we compute that again from the same measurement, okay, from the measurement taken in A, okay, that photograph. But whilst exploiting the fact that we already know um, the position, sorry, we already know the shapes of the objects in the room. And the shapes of the objects in the room are basically can be reconstructed um, using um, the original algorithm that I explained earlier. Okay, so once we figure out the ranges, okay, that's kind of solving the so-called nonlinear inverse problem, we can get E and then combine that with our color estimate or the shape estimate from the previous step um, to get a full 3D reconstruction. Okay, so that's a that's in a nutshell how we achieve this. And in fact, we were able to push things a little bit further by imposing smoothness. Okay, so the initial reconstruction was trying to impose sparsity. Okay, saying that rooms are mostly empty. Um, there are also ways of saying, hey, we know that in real life objects are mostly smooth, right? So they're mostly kind of the same color, uniform color, with abrupt changes. Okay, so one could impose that type of um, prior, so-called prior as well. Okay, in trying to compute a solution. Okay, so by imposing those smooth, so-called smooth prior, we got a much improved reconstruction, which is shown in F. Okay, you see this 3D, sorry, on slide 45. Okay, image F on slide 44 or 45, um, we get this reconstruction that shows again some mannequin that's white, a kind of circular ring thing that's blue, yellow, orange if you want, and then there's an orange blob, yellowish orangey blob on the floor. Okay, on the lower part of F. Okay. Okay, so I haven't shown you the ground truth yet, side by side with the reconstruction, but we'll see many scenes, example reconstructions, and that this will kind of take me to the end of the talk. Okay, so in the results on slide, actually, the setup in my lab on slide 47. So we have a setup. You can see an actual setup for where we conduct our experiment. So our room is we have a room. We made a cartoon room inside of a room. Okay, we didn't have enough space to kind of use the entire room, so we made a smaller room inside of my lab. Um, in that space, we have a camera that's looking at the ceiling. We have a hidden scene, and then you can see in blue dashed lines the occluding edge. Okay, so the wall and the kind of the doorway. Okay, and then on slide 48, you can see a reconstruction side by side with the true hidden scene. So on the in the first column, top of the first column, you see the measurement, um, and in the bottom of that first column, you see the true hidden scene that created that measurement. Okay, that observation, that photograph. Um, And then on the right, you can see in the second column, you can see the reconstruction that we computed using the so-called sparse prior, so the L1 prior. And then on the far right, okay, so the third column, we can see the reconstruction um, computed using a smooth prior, the so-called total variation prior. Okay. Um, so you can take look at those pictures, and for me, I thought this was amazing, right? So we can see the shape of the pose of that mannequin when we compare it to the ground truth. We can see the tube, we can see the ball, which is which is tiny, which is small compared to the rest of the things in there. We could still see it. Um, And we could even kind of make out the blue regions of the tube. We can make out the yellow regions and the portions that are slightly tinged orange, we can make out. And these are finer details that we can pick out. Okay. And we tried this out with many different setups. On slide 49, there's another setup that involves a shelf, four basketballs, and so on, many different colors, and a chair. And we can actually reconstruct those things quite with those objects quite well. Okay, and in slide 50, um, there's another reconstruction, and this is of USF. Well, the USF is my institution, the university where I run my lab out of. And again, here we see these reconstructions of the letters U, S, and F. Um, and what I found surprising is that there's a mannequin sitting at the bottom sitting on the floor. Okay, its contribution is pretty weak, but we could still pick out that mannequin's presence. Okay, so that's kind of in a nutshell an overview of how we achieve this idea. We tested out our algorithms under many different under many different scenarios in ambient light. Okay, so we introduced ambient light and tried to see how well our algorithm still works. And on slide 54, the bottom row, you can see a four photographs of the ceiling. In the first one, the shadows are they're pretty faint, but you can still see them. Second one, I can't really see much, but maybe there's some shadows there. The third one, there's definitely I can't see anything, and the fourth one's pretty hopeless. Okay, so we tested out these four scenarios. So where there's high ambient light, medium amounts of ambient light, low, and then no ambient light. Okay, of course, in no ambient light situation, that's where we have the best measurements. The shadows that we're exploiting to do imaging are more pronounced, and we do accurate imaging. Okay, and that's shown on slide 55. If we go to slide 56, we can see the results start to sort of degrade. 57, there's no, in slide 57 in the measurements, looking at the measurements, I don't see any penumbra or any shadows there. Um, but we still get fairly, promising reconstructions. At least we can tell there are two objects in the room. We can tell the color at least of one of the um, of one of them. The other one is kind of tinged a different color. Um, but we can tell where they are in 3D. We can tell, at least in one case, we can tell its pose. It's holding out a T pose. Okay, holding its arms out. Um, and the final fourth case, okay, where there's huge amounts of ambient light, the algorithm basically fails. Okay, so um, hints for you guys who may be worried about being spied on using this type of technology. Um, you know, it'll fail in very high ambient light. Okay, so when there's huge, say, sunlight, okay, out in the broad daylight, um, this technology is still kind of not robust enough to handle that situation. Okay, so why did we get these results? The idea is that there's information in these shadows. Okay, so information in shadows that we captured in a photograph. It's a 2D photograph, and we can actually exploit all of that information if we do it in an informed way. If we do it in a carefully um, take a carefully crafted approach, we could actually exploit that shadow to reconstruct 3D information. And this is just from a 2D photograph, right? So going from 2D to 3D is so if you even with line of sight is a challenging problem, uh, but we do it without line of sight, right? Okay, so there are some mathematical techniques that are used, at least in my lab, to analyze how difficult or challenging a problem is, and this is so-called Fisher information analyses. Um, and the core idea for those who may be interested is kind of summarized on slide 60. Okay, and the key thing I wanted to share is at slide 62. Okay, in slide 62, we see three scenarios. One is labeled no edge, and then the second one is labeled one edge, and the third one is labeled two edge. Okay, and the so-called Cramer-Rao bound tells us how, basically tells us the uncertainty of estimating some unknown given a set of measurements, okay, given some scenario. So in the first scenario, as you can imagine, as its name implies, where there are no edges, where we're not exploiting any edges, and we're trying to reconstruct a certain point in the hidden scene. We basically, that point, okay, imagine you can see an ellipsoid in that room. That if we try to reconstruct the position of that point um, from um, non-line of sight measurements, okay, um, we would make an error that lives inside that ellipse. Okay, so we would be confounded essentially um, in a way that makes us think, make errors that somehow live inside that ellipse. So we would get very essentially the idea, the key point is that we would get imprecise reconstructions. Okay, we'll make very large errors. Okay, if we want to exploit it one edge, then we would still make errors, but along certain directions. We can see that that one edge case gives us errors in the YZ plane. Okay, along the XY plane, there's still a large error along the range. Okay, so along that blue line, there's an error, but the error collapses essentially to a line. Okay, so basically we know the angle, the azimuthal angle, so the angle that pivots around the origin, okay, along the floor, that we make almost no error. Okay, we can get that coordinate precisely. Whereas every other coordinate, there will be some error. So the range has the largest error, and the other coordinate will have a large error. But if we introduce the second edge, so the vertical and the horizontal edges, we see that this ellipsoid, okay, now collapses to basically a line. Okay, so we have a line that basically we make an error. The error we make along the azimuthal angle is very small, so it's a line along the along range. Okay, so the azimuthal angle um, um, pivoting around the origin um, along the floor, basically there's no error there, or very minimal error. And similarly, the red also collapses to a line, so that red ellipse now collapses to a line. Um, and again, there's a small error, okay, in angle that pivots around the vertical edge of the door frame. Sorry, around the horizontal edge of the door frame. So the most substantial error is along the so-called um, major axis of that ellipse, of this ellipsoid. Okay, it's very thin, it's like a really small, but this is a small error. So basically we can more accurately localize a hidden scene point. Okay, so that's the core mathematical kind of uh, the mathematical framework that led us to thinking about the best coordinate system for this problem. I've left out a lot of details, and a lot of that can be found in the paper. And obviously, I'm happy to answer questions following um, uh, following this talk or here as well. Okay, so if you look at the paper and you have any questions, you can reach out to myself or my graduate student. Okay, so I'll conclude by saying, well, we've been staring at shadows. Maybe you've been staring at some shadows kind of following the eclipse today. Um, Here we were able to see that shadows can lead to 3D imaging without line of sight. Okay, and in our case, we essentially were able to do this by exploiting information orthogonal representation, the so-called projected elevation spherical coordinate system. Okay, and our approach gives us some robustness to ambient illumination, but we want to extend it in a way that would be amenable to application in kind of daylight situations, so situations in the wild. Okay, and essentially here we're exploiting the edges that are created by a door frame, okay, the opening of a door frame, and that door frame is was visible to us on the visible at the observer's side. Okay, um, we want to be able to uh, somehow extend this to arbitrary occlusion. So perhaps situations where we don't even know what's casting the shadow. Okay, so we don't know what's causing the obstruction. In this case, we know that it's a door frame. Okay, it's the wall containing the door frame. Okay, um, but there are situations where we can't actually see those occlusions, so we don't know what's casting the shadow. And this is more broadly applicable to real life situations. And we believe that the tools that we've been able to develop here to allow this kind of this to realize this current work are able to enable us to do this even in these more challenging scenarios. And we have some preliminary results which I've previewed there on slide 63, the figure on slide 63. You can see a new setup um, where everything is hidden. The only thing that's visible is a wall in front of us. And we just want to use light reaching that wall to do our reconstruction. Okay. So that's the in a nutshell this work, um, and I'm happy to now take any questions.
Yeah, thank you so much, John. And yeah, what a very detailed slides that you had shown us, despite the also Clubhouse being just an audio app. You were able to show in your slides very comprehensive figures and calculations. So I would like to announce to the audience that we are opening the floor for questions or clarifications. Um, and so, before that, anyway, I'd like to introduce our guest speaker shortly for those who just came in. So, Professor John Murray Bruce received both the mechanical engineering degrees that he has with honors in 2012 and the PhD degree in 2016 in electrical and electronic engineering from the Imperial College London. And while at Imperial College London, he received the Institute of Engineering and Technology, or IET Award in 2012 for Best Overall Performance in the Mechanical Engineering degree, and the Maurice Hancock Award in 2008. On March 2017, he joined the Electrical and Computer Engineering Department of Boston University as a postdoc researcher associate. In the spring of 2020, he joined University of South Florida's Department of Computer Science and Engineering as an assistant professor. His research interests are in computational imaging, vision, and inverse problems. So yeah, I'd like to ask anyone now who would be interested to come up here on stage to ask questions. You can raise your hand. So I would also like to welcome Hansen here, our regular moderator here in Quantum Photonics. So yeah, just flash your mic, Hansen, if you have some questions, and also you, Bob. So I see Kevin also raised his hand, and I think earlier there was Nas who was here. So yeah, Kevin, would you immediately like to ask a question before us? I will give you the floor now because I know you had been patiently waiting.
Oh
Thank
yeah,
you
hi.
so much, Cecile. Hi, Kevin.
Oh yeah, I missed. I couldn't access the slides, and I missed a lot of this. And the Final Four is going on. I guess I'm distracted, but technical problems. But I still seem to have a lot of questions for this one. Maybe I'll just say some of them. I think I heard you're using just a regular digital camera device, but do you think you can combine this with other electromagnetic techniques, to
That's a
see
great
through objects around? Oh, I'm
that's a
sorry.
great question. Actually, that's a great question, and multimodal imaging or multimodal non-line of sight imaging is an kind of one direction where we're taking this along as well. So I think that there's a lot of potential to get more information by combining different sensing modalities. So this is one sensing modality. The key challenge here I wanted to achieve was to see if what could be possible with an ordinary camera, to essentially explore the limits, the very limits of what we can do. Okay, and you know, to begin with, we didn't think 3D was possible, but you know, and nonetheless, we pushed forward and then decided to kind of do in-depth analysis of the 3D situation to get to where we are. So now that we fully kind of get a better handle, if you want, for the 3D case using ordinary cameras, so we know what the fundamental limits are, so that means, you know, this is the best we can possibly do given what we have, the current devices that we have, current cameras that we have. Can we look at other devices, figure out their fundamental limits, or other sensing modalities, figure out their fundamental limits, and combine them in a way that would kind of go beyond um, the sum of their parts, if you want. Okay, so I think it's a great question, and I think there is a lot of uh, room to do this.
Oh, okay. Yeah, I was just thinking of like radar technology and X-ray, infrared, long wave, infrared imaging, and
Right.
then I was just wondering, have you thought about using different? I know this is all this would take 10, 20 years. Have you thought? I'm sure you thought about all this, but you know, using different materials, you know, or different even angles, like you said, you use the door frame, gases, you
Yeah.
know, fields, magnetism, you know, to 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 amplify the signal.
So those are also great possibilities. So I guess my when we talk about electromagnetic waves, I'm uh, you know at least that's still in my expertise. When we start deviating from that, then things start getting further away from my expertise. But if there's an expert in other, you know, other types of um, uh, people who are used to dealing with other types of signals that are different from electromagnetic waves. Yeah, I'd love to talk more and explore possibilities of being able to exploit or leverage those modalities. But I haven't done that. I've worked with visible light pretty much. So in this and our initial work, so some prior work is focused on using time of flight methods, so the methods that essentially send pulses of laser pulses, ultra short laser pulses, into the hidden scene. So by reflecting off of a visible surface. Um, so we've used that. We've used ordinary cameras without actually emitting any light into the hidden scene indirectly, and just using whatever existing light there is. But we've not explored situations that you're suggesting, um, Kevin.
Okay, then maybe one more thing is maybe just you know just and then if it gets more complicated, you know, like sci-fi, then they can use techniques to jam, you know, jam the signal coming from the
Right.
source and stuff.
Absolutely. So then you can think of ways to avoid being detected, right? So that's the converse of this problem. Um, right? So how can you jam the signal, and what can you do to maybe even better, if you jam it, maybe people know that you're jamming the signal. But even I imagine now that maybe one interesting thing to do would be to perhaps fool them into thinking there's something else in the room, right? So you project onto the ceiling or whatever it is you want to project, um, or the floor or on other surfaces, you project a kind of shadow distributions that fool them into thinking there's something else there, right? So you can make them see what you want them to see, right? So, and I think that that's a particularly clever way to like obscure um, or hide, right? Um, but yeah, it's great questions, Kevin.
Yeah, thank you so much, Kevin. So I'd like to ask, what are the key challenges that you foresee in refining the algorithm to enhance its speed and accuracy? And how might advancements in computational power and machine learning further enhance the capabilities of this algorithm in the future?
That's a great question. So the two parts or two-part question. So let's I'll tackle the challenges first. So the key challenges in extended this to kind of work in reality. So I've alluded to the fact that ambient um, illumination, so bright, say for instance, daylight um, makes kind of the system is not robust to operate in bright daylight. Um, and the key idea there is because of limitations in our current sensing technology, so how cameras currently work, they have a finite kind of dynamic range, and the signal that we're interested in is buried in really bright light. So it's something like 0.01% of um, the light that the camera captures is what is the useful information that we want. Okay, so and in broad daylight, this even gets lower, right? So it's even more challenging to pull out those signals, especially using current detectors. However, we can design new imaging systems that essentially cancel out or reject um, bright light sources and constant bright light sources such as the sunlight. Okay, so there are new ways to kind of design optics that can reject ambient light, and we could exploit that. Okay, so that's one way forward in tackling that challenge. In terms of speeding it up, um, computers are getting faster. We could potentially build a faster algorithm using Python or even faster programming languages out there. Um, and these algorithms that solve the problems that we do, actually, our system is pretty much um, we, has some optimization already for speed in the sense that it um, instead of solving a 3D problem, which is directly, which is highly complex, so you need more storage and more computational power, we solve a 2D problem and then another kind of one-dimensional problem. So we solve the 2D reconstruction and then compute a range for each object. Okay, so that's a simpler way to go about it instead of solving a 3D problem right away. Okay, so we're already benefiting from that improvement. Um, but yeah, so some of the key challenges, if you want to scale this up, you need a faster compute. If you want to, for instance, if you want a 4 megapixel, we're used to seeing megapixel images, right? The images I showed to you in my slides are something around um, a few thousand pixels. Okay, um, we want to push this to that megapixel regime. And to be able to get there, we need to kind of innovate on storage, and that's where machine learning could come in. Could come in. Okay, so machine learning, these networks give us a nice way of encoding 3D um, structures in a very compact form. Okay, so some of you may have heard of NERF and SDFs, so signed distance fields. Um, some of these machine learning models out there. So, for instance, there are also language models that have been large language models, such as the foundations of ChatGPT and so on, have been exploited in imaging. Okay, so and 3D 3D photography to represent 3D objects, okay, in a very lightweight uh, form. Okay, so we can exploit some of these things and kind of infuse them into our pipeline, which is currently just, you know, a that doesn't use any learning. Okay, it doesn't use any machine learning, but we could somehow actually in a nice way we could incorporate um, models that have been trained to understand 3D world, okay, 3D models, create 3D models. We can use them to um, and infuse them with our approach to create like a physics machine learning hybrid to do this. Those would speed things up as well as give us possibly better pictures. Okay, so it's a great question, Cecile.
Yeah, thank you. And there was someone who raised his hand, but I'm not sure
Actually, I
if.
have some questions. Hi, John.
Go
Hey,
ahead,
Hanson.
please.
Hi, John. Thank you very much for the presentation.
Thank you.
I understand this is a kind of a basically an ill-posed problem, and
Yes.
the and actually the I would say the worst kind of ill-posed problem because you
Yes.
basically, yeah, you can have in I mean some ill-posed problem is you do have one-to-one correspondence. It's only the condition numbers
Exactly.
are large, and then computational hard like a heat equation, and
Hmm.
try to figure out the source. But
Hmm.
this problem is basically you have it's a many to one
Yes.
function. Yeah, so basically, you have many uh, images, original sources can
Hmm.
produce exactly the same image. And then, so as to Calvin's original question of whether you can jam it, I mean, it's better, you can do better than that. You can just, because it's a multiple, has multiple solutions, you can just, the, uh, make up the source easily. And right, so
Yeah, I see what you're saying. Um,
and
yeah.
and then so I understand that you want to do the regularization. So to, for example, to L1 size
Hmm.
to say assuming that penalize large size
Hmm.
objects, and
Hmm.
then you can do the derivative. I mean, let's say first difference, first order difference,
Hmm.
second order difference, so
Hmm.
that the surface could be smooth
Smooth.
and all that to right, to limit the range domain of
Hmm.
solutions.
Hmm.
Uh, yeah, and then basically you can distinguish if they belong to different very distinct categories of solutions or equivalent classes of solutions, and so and then I think the bright light source
Hmm.
confuses the solvers. I
Hmm.
mean, you can have. I think you assume that the light the wall of the room is kind of matte and then
Yes.
uh, yeah, low reflectance, right? So, but the thing is, if you have bright light source, then you have will have multiple reflections, and then basically that that in equivalently basically enlarges the solution space. That because you can think of if you put the mirrors on the wall,
Hmm.
and so any object in one corner just reflected the infinitely. I mean, depending on angle of the walls, and so you're going to have multiple solutions, and the when it's dark or when its reflectance is small, then there's no multiple reflections. Then basically the light source, it's only the one coming from the object is the light source,
Sure.
right?
I see what you're saying. Um, that's a good point. One thing I wanted to to point out is that when you have mirrors versus matte surfaces, I mean, if you had mirrors, the problem
Right.
is
No, I mean,
trivial. If
I'm saying that, yeah, if you have mirrors, I'm going to say that basically you can have images coming in, and you can, in that sense, in that direction, you can figure out what
right,
the rise. But I want to emphasize the multiple reflection. But you can easily make, the wavy surfaces, a random indentation on the mirror, and then you
sure,
can have reflections, and then but it reflections goes everywhere
I
randomly
see.
but then
Yeah,
yeah.
no, I think I get your point. With matte surfaces, though, each reflection significantly weakens the signal. So the first reflection, here the pretty much after the first reflection that comes to your camera, um, everything else is super weak anyway. Even in the bright, even in the dim case. Um,
Yeah, because there's no multiple reflection, because once it decays fast, right? Because it
right.
absorbs, right? Yeah.
Even in the in all cases, it will, it's just the relative, right? Even if it's dim, okay, if the
Yeah.
hidden scene is
Right.
dim
Exactly. So
versus
it's the
bright, it
reflected, yeah, the ratio of intensity of reflected light to the original
Mhm.
light that matters.
Right,
Yeah.
right. And for us, it's the what kills what kills kind of the algorithm, or rather the um, the limits of our approach is um, kind of set by the light that comes from the visible side. Okay, so everything from the hidden side will be informative, whether it's multiple bounces or not. It will be super informative because those multiple bounces anyway just bounce off of the hidden scene and come towards the visible wall or ceiling. Um, and you know, in that case, it doesn't really matter as long as you're reconstructing the entire hidden scene. Um, then everything is kind of you're in a good situation. If your hidden scene is much brighter, but if your visible side is a lot brighter than your hidden side, that's where the problem comes. Okay, so that's where the surface that you see gets drowned out by the visible side light. Um,
When you say visible side, you mean the light? I mean, the target is completely hidden, right? Is that correct? Target is
so
completely obstructed, right? No.
so the target is completely obstructed, and that emits, essentially they reflect light um, some towards a visible surface, say the ceiling or a wall or somewhere. So the visible side that I'm referring to the visible side as the side that you're standing in. So this is the region, everything that's in the region that you can see. Okay, so
Right.
everything that you have line of sight to. Okay. Um, Whereas the hidden side are all the regions that are hidden from you, from your direct line of sight.
Yeah. Because yeah. Right. I mean, because I mean, basically, but the thing is, if you um, basically it, I think it has to do with the dynamic range of the
Yes.
I
Yeah,
mean the
yeah, yeah.
CCD
Exactly.
device,
Exactly.
and yeah.
Yes. Exactly. It's just the dynamic range of your CCD. The information is there. It's whether you can measure it. That's right.
Right, exactly. And then of course, I mean, if it's so light, so bright that exceeds the CCD threshold, then nothing will be reviewed.
Right.
And
Yes. So you saturate everything. Exactly. That's right. Whereas the signal that you care about is the one that kind of sits on top of the really bright signal, and it's just kind of tiny variations on
yeah,
top of the very
so it's
bright signal.
superimposed, yeah, kind of
Exactly.
because everything's now. I suppose that you're doing everything linear, right? Then you're so
Exactly.
superimposed on, right?
Right.
And So, I mean, I think you, one question though, I mean, do you know the dimension of the room, the walls
No, no,
and the,
we don't know the dimension of the room. We don't know. The only thing we assume we know is the door frame, because we
okay,
can see
so,
it.
but do you take so basically you're inversing the object, everything behind the door frame, right?
Exactly, exactly.
Um, okay. Uh, yeah, right. So it's not knowing that you view everything behind the door frame
Mhm.
as the target, right?
Exactly. So we just treat everything behind the door frame as a target, and we just want to figure out where things are in space.
Right. So basically, uh, but and then yeah, I mean you could do an arbitrary shape of the room, right? Um,
Yes,
yeah, the yeah, I mean, but then it takes taken care of by the regularization. Um,
exactly.
uh, Right. So,
Ex-
and then you basically the forward kernel
mhm.
in the is or matrix is the ray tracing kind of um,
That's right. Equation.
visible optics, right? Equation. I mean,
Yeah, yeah, exactly.
one over r squared or
Exactly.
and
One
then
over r squared.
cosine.
Exactly. Cosines
Yeah.
for the viewing angles and so on.
Right.
Yes,
Right. Okay.
that's
Cool.
exactly it.
And then
Yeah, yeah. There's
but then do you let me think. Well, okay, so it's a color camera, right? Color
mhm,
camera, and I suppose if you actually put on a polarizer, I mean,
mhm,
but of course, I mean, you only take one picture. Let's say if you take any number of pictures you want, but only sitting at the same angle, same position. Uh,
mhm.
but you can take any picture, a number of pictures you want, and then you put a polarizer in front of the
Yeah,
camera, and then you turn the polarizer, you know,
yeah.
maybe
That's a
4 degrees. I mean, like equally
four different
uh,
angles.
4 different orthogonal,
Yeah,
or 45-degree angles, and then I'm sure you can invert more.
that's a good point. You know, I haven't explored this. I know um, there's a line of work that extended one of my previous approaches to do this. So the 2D case that showed that they can get slightly better reconstructions if they use the polarizer in the way you mentioned. Um, so it is uh, it is possible um, that one can get a bit more information by doing that. It's a great trick. Um, we haven't actually explored that, um, but someone did it for one of our previous approaches for the 2D for doing 2D reconstructions. Um, I wonder, how much additional information it would bring in this case. Um, but I'm also a little bit feeling maybe a little bit pessimistic in the sense of how much additional information we could get. Um, but I don't want to speculate just yet too much as
Well,
to
that's true. I mean,
yeah
the thing is, it depends on the light source. If the light source
yeah
is
it's
incoherent light,
polarized, right.
yeah, if it is incoherent light, let's say the direct sunlight shining in, or some the instead of instead of let's say reflected sunlight
Hmm.
off the ground, then it's
Yes,
polarized, and then
yes.
but if it is direct sunlight shining in, then you have incoherent light, and then it
That's a
won't
good
help you much. Yeah,
yeah, that's a good
unless
point.
the object itself or the the room
Hmm.
walls are kind of a little bit of a different material, and
Hmm.
then reflectance and then the wavelength, the polarization off. I mean, when you reflect it off, will change. And I mean, yeah, some direction is more preserved than other direction. Then you'll have more information.
Yes, so thank you, Hansen. And yeah, I would like to say that we've been here for about a little over 2 hours now. So I'd like to ask John. Usually we ask this question at about 1.5 hours, but now I'd like to ask you how much more time do you have for us?
I think I can take a couple more questions and then call it there. But I don't want this to be the end. Of course, I've enjoyed it. But please feel free to message me additional questions, and I'll be more than happy to answer them or chat more if people have additional questions or just want to chat about the work or indeed about quantum.
Actually, I have one more question. So the if I understand that you do this kind of in the good old linear algebra and the
Hmm.
mathematical point of way they approach. Let's say if you use neural nets and then
Hmm.
uh, it will. I mean, of course, you need to train a little bit, and then um, because it's basically a universal approximator, and then
Hmm.
you probably don't need to know the physics. You probably don't even need to write out the kernel cosine theta over one over r squared, and then
Yeah.
just kind of a dumb in a like no brain and the
No, no,
exercise.
you know. That's a great point. So I'll tell you, kind of give you a bit of insider information. We did try a lot to 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 solve this just using good old, well, it's good old. It's still new, right? So good new neural networks. Um, so where we collected a bunch of data set, trained, you know, and we didn't have much success. Um, and the one, I can speculate a little bit about why it didn't work. And I think some of that is to do with the fact that these neural nets adapt, they're very good at like learning the most obvious signal, right? The signal we care about is the one that's kind of buried underneath this, dominant one, right? So it would take a ton of data set for it to start fitting to that. So that's one, one I think kind of hand wavy, if you want, explanation to it. Of course, until we're able to fully lift the lid um, off of how these neural nets really work. Um, you can say everything is just kind of um, uh, somehow informed speculation, if you want. Okay, so we could try to say avoid learning the physics by using these neural nets, and that's fair enough. Um, I'm a big kind of proponent for, hey, we know the physics. We've spent you know centuries trying to understand physics. If we know physics really well, at least the physics that we know really well and can model really well, there's no reason to then try to gather data sets to train a neural net. Okay, so that's one thing. But that doesn't mean there aren't uses. In fact, we are exploring uses of neural nets for this problem, um, and only when we kind of had a breakthrough in how we modeled the problem were we able to actually start understanding how to make neural nets work for us. Um, in solving this problem. Okay, so yeah, so that's you know, it's not that it's just one needs at least for me this gives me hope. It means that those of us who are not building neural nets on a daily basis, will still have a job, because it basically meant that we had to somehow understand the problem and be able to solve it using standard good old linear algebra physics, um, uh, to be able to then develop neural nets that could actually be effective.
Yeah, actually, it's not. I'm not completely. Uh, let's say I'm not too surprised by this, and I
Mhm.
was kind of secretly kind of anticipating that.
Okay.
Yeah, so because I do, I mean, I do think that I always have this doubt that whether neural nets are completely, so yeah, it is a universal approximator, but how effective it is, I always had the doubt. And then this
Yeah.
is a good. Actually, I want to ask you how much training have you done with the neural net? And
Okay.
so then, I mean, I just want to kind of be a devil's advocate, saying that is it because that you didn't train enough or not enough data, so
I,
that it's not the incompetence that I was secretly hoping for of the the neural net.
I will I will say that we um, it's definitely a combination of both, and also a bit of um, I, so a combination of both not training for long enough and um, not training with enough data. And by that I mean at some point we needed to give up, right? So at some point we need to go, okay, this is obscene amounts of data, and we can't spend all of our time just collecting data. Um, we need to actually move the research along, right? So we needed to draw the line somewhere, basically. Perhaps if we just kept on going with more data set, with more training, maybe we would have nailed the problem um, in a different way than we do now. Um, but I would say that for a similar, for a related problem, so still non-line of sight imaging, but with a different configuration, we spent about a year and a half, trying actively all sorts of variations of neural nets, different models, different architectures, um, all sorts of data sets, different augmentation styles and strategies, um, to try to make it work without much success. Um, and now that could just be we weren't lucky, because there's a little bit of an element of luck when you're training a neural net, right? So, um, and picking the right network and network architecture, um, that's still kind of an art, right? Some for some problems, it's well known that certain architectures perform well, um, but in this problem, we don't know what's the best.
Yeah, on that regard, the I think one thing that it can be helpful is we still retain the kernel, basically
Hmm.
Maxwell's, I mean, approximation of
Yes,
the Maxwell equation, cosine over r squared.
yes,
But one place that can help is the regularizer, because
yes, yeah, yeah,
the
yeah.
usually yeah, the regularizer, the go-to one would be L1, and or the
Mhm.
delta U L1 or L2, or
Exactly,
the lasso, whatever
exactly.
the combination. I mean, the convex combination of L1 and L2. But I think that this is it's the only. I mean, this is for the computational convenience. But I mean, the prior information that is injected into the problem, I would say that which should be the range. I mean, the domain, and it should be
Yes,
more richer than the size and the smoothness. Maybe
exactly.
that, yeah, that if the the neural nets can approximate more effectively approximate the complex functions, then let it be the regularizer.
Yeah, yeah, yeah. Absolutely. I think you're spot on. I think yes, that's where we could help. And I think my students are actually exploring this. Yeah. So my kind of I let them explore, in this way, in the sense that I kind of think of the kind of larger problem, and if so that if they want to explore neural nets and other extensions, that's nice. I'm happy that, hey, we were able to solve the problem. So now we know at least the problem is feasible, right? How far can you push it using um, neural nets is another question. So that's a great point. We're at the kind of fundamental limit using standard physics, exploiting neural nets as regularizers, um, so as priors. That's a great point. I think that one could get potentially a performance boost from doing so, especially in the low noise regime as well. So sorry, high noise, high ambient light regime.
Right. Yeah. Great. All right.
Thank you.
I got one more quick question.
Yes, Kevin.
Do you guys know yet if uh, biological or organic sources, if that matters, because they have auto fluorescence, if that matters for the what the sources.
That's I can't say we've thought about those. Um, but I'd be curious to hear more about along the lines of what you're thinking. Um, I'm not, I'm not particularly clued up on uh, bioluminescence and the kind of physics or biology, if you want, behind those that phenomena. But I think you'll find information in the most in kind of the least likely places. Well, because we've not been looking. So this could be it could be a great connection, right? There could be a great connection there, because you know, it, thinking that shadows could provide so much information initially may be skeptical, but I guess um, hopefully some of the work that we've done is kind of shown that's possible. Um, so yeah, it may well be this is another potential source for information.
Yeah, I would just like to. Evan, are you still speaking?
Oh no, I'll just say I'll look into it more and maybe get back to you, see if I can contact
Yeah,
you or something. See if I can
that
find
would be
anything.
awesome. Yeah, yeah.
All right.
Yeah, thank you so much, Kevin. Yeah, before we close, I would just like to mention that, of course, some of our eureka moments to solve, we always continue to ask questions, even if we have solved problems. But some of our
Exactly.
eureka moments are not necessarily linear. Sometimes they could be exponential and they could bank on the work of other people who might have the
Exactly.
technology that we don't know of that you can use to further
Exactly.
your research. And I would just like to mention that maybe 2 years ago, if Hansen remembers that, he wanted to invite Anima Anand-Kumar of Caltech, but her partner in this research, Kamyar and Anissa Denishelli, came here to talk about their research on neural operators. And
Right.
at that time, they were using neural operators to do mappings between function spaces, which makes the discretization invariant, meaning they can work
Okay.
on any discretization of inputs and to converge to limit this on the mesh refinement. So that was the first study that they made, I think, also together with NVIDIA. And later on, they were able to, on the next year, they were able to train, they extended it to physics-informed so-called neural operator. And this time, I
Right.
think there's a third level, and probably, this can be very useful for the research of
Yeah, yeah, yeah,
John
yeah.
in the future. And
Yes,
I also
absolutely.
remember, you remember that, Hansen? Yeah, so there is also the research of David Ha of Google Brain, I think 2 years
Oh,
ago as well, about sensory substitution. So, meaning to
okay.
say, all these researchers are looking for things that could not be seen. However, sometimes the use cases may not necessarily be the literal ones that are being studied on that particular case. I think that probably if they try to work with you in the future, you can
Yeah,
make,
yeah.
you can bring research to a
Connections. Yeah,
higher
yeah.
level.
Yeah, absolutely. So I've been following some of the work of Anand Kumar at Caltech. But yeah, I think that's a great point. One often, it's good to maybe every now and then go back um, and look at things that we've done. In fact, a lot of the foundations for the so-called information orthogonality, it's not very well known, um, but I found an old text from, what was it, 19, I think 1930, um, that talked about some of these ideas, but in a different setting. Um, so and they, we I guess there was no, maybe they didn't have nice applications, but we have a problem that really needed it to work. Okay, where we really needed that type of framework for it to work. So that didn't, well, I guess what I'm saying is just to kind of echo some of the stuff you're saying, Cecile. So yeah, it's great.
Oh, speaking of information orthogonality, you said you're using Fisher information. I'm
Yes.
wondering, yeah, I'm wondering if the Fisher information itself is used in your inversion, or is it are you using it purely as a kind of an error, kind of an interpretation
So,
of
oh, so,
information,
no.
or are you
That's a
using it as
great
a
question.
regularizer?
So, no, no, we don't use it as a regularizer. What we use it to do is to um, find this, the kind of what I call a coordinate system that is natural for our problem. When we tried to solve the problem in Cartesian coordinates, it didn't work. Tried many other different coordinate systems. Well, actually, we tried Cartesian coordinates and one other, um, and we didn't get the results that we thought we should be getting. Um, we use the Fisher information to craft, if you want, this coordinate system that we use. So this projected elevation spherical coordinates. Um, so that was our use for the Fisher information. And why did we do that? Oh, so the Fisher information tells you essentially the information about each parameter that you're trying to estimate, about the information contained in your measurements about each of those parameters that you intend to estimate. And basically, if you represent your unknowns in Cartesian coordinates, we find that the Fisher information matrix um, is you get this diagonal matrix. Sorry, no, it is non-diagonal. So in the sense that it's still positive definite, but if you could find a new coordinate system where your Fisher information matrix is a diagonal matrix, um, i.e., that tells you that all of your parameters are independent. So errors in one parameter will not affect it will not cause an error in a different parameter. So in this way, we could say fix the range to any random parameter, even any random value, even though that value is wrong, and still be able to recover all the other parameters correctly. So the angle and in theta, so the azimuthal angle and the projected elevation angle. And this property only holds true for our problem. This property only holds true using the projected elevation spherical coordinates. Whereas if you did it in Cartesian coordinates and you, for instance, picked the wrong x, your y and z estimates would be correspondingly wrong. Um, whereas in our coordinate system, picking the wrong range rho did not have any impact on the shape estimation. Okay, so that's the um, kind of a deeper take, if you want, at what we were exploiting.
Okay, so I guess maybe the kernel is mostly concentrated, but not exactly, but mostly
Yeah,
concentrated on the diagonal.
along the
Is
diagonal,
that correct?
exactly. Yeah,
But
so
not
if you,
exactly, right? But it's concentrated. Is that correct? Is that a
yeah,
correct?
so it's almost diagonal, yes. So it's approximately diagonal. Yeah.
Cool. And then just quick, the in the question, the elevated, the projected elevated spherical coordinate. I mean, it
Hmm.
is a spherical coordinate. Elevated, is it elevated when the origin is dependent on the elevation of the camera, or what
Oh
is the?
no, so the
It is still a
yeah,
spherical coordinate, right?
it's it's a kind of a weird spherical coordinate system in the sense that in the standard spherical coordinates, you have a polar. You basically have a range, an azimuthal angle, which is just the angle projected onto the floor, right? Um, we use the angle projected onto the floor and the angle projected onto a kind of a vertical plane. Okay, so the xy plane projection, so that's the usual theta angle, the azimuthal angle.
Yeah.
But instead of taking the um, elevation, okay, the usual elevation in spherical coordinates, we basically project that elevation angle onto the x onto the YZ plane.
Oh, okay, I see what you're saying. Basically,
Yeah.
it's not the if I can still use the z coordinate. I mean,
Yes.
the elevation theta is the this vector from the origin
Hmm.
to the point of concern. The
Exactly.
That's theta, and then you have a
Yes.
projection onto the xy plane angle. But then you're saying that instead of using the theta between the vector and the z axis, you're
Exactly.
using the angle of that theta projected
Proje-
onto, let's
projected
say,
onto
xz or
exactly
yz plane, right?
YZ
Okay, got
YZ.
it.
Yeah, yeah,
Oh,
yeah.
okay,
Exactly.
yeah, I got you.
Yeah, yeah. So it's a slightly different spherical coordinate system. So we just called it projected elevation because we're basically taking the standard projection angle and projecting it onto the YZ plane.
Yeah, gotcha. So basically, the reason it makes the computation, um, yeah, I can see why it's the
Yeah,
Fisher
yeah.
information is different because it is less sensitive when uh, the phi is, let's say,
Yes.
zero, and then yeah, and more
Yeah.
sensitive when the phi is negative, right? Yeah.
Right. Right. That's a good point. So it's like there's a rotation around the horizontal edge and the vertical edge
Right, yeah.
of the door frame. Yeah. Well, I didn't think my talk was as effective, Hanson, as in the sense that, or at least this gives me more confidence that the questions that I was asked today, um, without slides. This is the first time I don't know what slides my audience is looking at, right? I just have to trust that they're looking at the correct slides. But this gives me great confidence that actually things were fairly effective. So thanks.
Yes, yes. Thank you.
Yes. So, Bob, you were about to speak.
Oh, thank you, Cecile. Professor, I'm curious about your camera. I'm curious about the resolution and the frame rate that you're using.
So that's a great question. We use a CMOS camera, just a standard CMOS camera. Um, well, I guess a scientific CMOS camera that's available from Thor Labs, uh, and it's I believe 5 megapixel camera. Um, I can't remember, but yeah, we downsample those measurements to 256 by 256 to 256 by 256 image. Okay, so we're kind of throwing away a lot of information, but yeah, this was just computational um, considerations. But otherwise, one could deal with the 5 million pixels and run the same algorithm. It'll just take a while, but you would get fairly nice results.
And
Um,
if you increase the frame rate, does it give you more information or too much information?
Actually, so we use a fixed frame rate. We use we take a single photograph, so we're not even taking. But if you wanted to make a video of the hidden scene, you could take a video of penumbra of the shadows and basically run our algorithms per frame. Okay, so in our case, essentially, it doesn't matter what the frame rate is. We're just because we're only working with a single snapshot. Okay. Does that answer your question, Bob?
Absolutely. Thank you very
Okay,
much.
that's good.
Excellent presentation tonight.
Thank you. My pleasure.
Yeah, thank you, John. So I think we're at the top of the hour, and I would
Yes.
just like to thank you for the great presentation and the great conversation. And we hope that we can invite you here again in Quantum Photonics, maybe to talk about your lab, your work, or yeah, another paper. We really
Yeah.
enjoyed your presentation today.
It would be
So
a huge pleasure. I enjoyed this.
yes, so in the near future, we'd like to welcome you to Starship Photon, one of the side projects of quantum photonics, which we hope will come into fruition. And so, yeah, we have here Darcel, who is the founder of the tech startup founder of Starship Photon. Can you say hi, Darcel, before we close? Even just hi.
Yes, I can. Hello, doctor, and I'm certainly feel very happy that she extended you the invitation to our project that we have going on behalf of us three, me, Bob, and Cecile, on behalf of the quantum photonics movement here. So I look forward to. We all look forward to speaking with you more on that. And in a great
No,
presentation, doctor, and very interesting. I have a lot of questions, but I know now is not the time about the pixels. When you said that 5 million pixels, that really got me. But we'll talk later. I'm sure. Maybe you can come back. And but that's it. And I look forward
yeah.
to speaking with you again, doctor.
Great to meet you, Darcel. It's a huge pleasure. Yeah, I'm open. Definitely would love to come back. In fact, it would be. I'd take it as an offense if I weren't invited back. Um, um, but no, I'd love to be back at any time, and everyone's been super friendly and great conversations, and super pleased that I was, yeah, super pleased to be here, and I generally could keep going because everyone's been, asked such great questions, um, but I fear I may not be functional tomorrow if I kept going, but this is great.
Yeah, thank you so much. So we'd like to thank, of course, our co-moderator here, Hansen. I'm always very glad if he's with us moderating the room because he has great insights and also wonderful questions that tries to uh, make the audience look at our conversations to be more interesting. So, yeah, thank you so much, Bob, of course, for always being here. And I think you are very interested because this is also your field, the topic of Dr. John now. And anyway, Kevin, thank you always for your support. So we're going to wrap up. And thank you, everyone. I cannot mention all of you, but I think I can. There's LT, Tomoko, David, Daniel, Lisa, Pinal, Pat, Gary, Jeff, G, Anthony, and Bida. So thank you so much. And I'd like to give the mic now to Darcel to help us close the room.
Thank you, Cecile, and Doctor. Thank you again for a great presentation. So to close the room, we're going to start our countdown from lucky number 6. Is everybody ready?
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 Route 66.
6.
6.
Kevin 5.
Oh,
Hanson 4.
4.
Bob 3.
3 it is?
Cecile Dos Equis.
Dos Equis.
Good doctor, your numero uno. Call out our last number, please.
1.
Thank you, John.
Thank you.
Yeah,
Bye-bye,
see you
everyone.
again soon. And good
See you
night,
all.
everyone.
Bye.
Remember
Thank
this
you.
important
Thank you,
room
John.
for the
Thank you, Ruby.
eclipse day.
Thank you all. Bye.
Yeah, good
cheers.
night.